It is a warm afternoon in June, 1955. A professor of theoretical physics at Princeton University pushes back his chair, walks to the window, and watches a group of students cross the lawn below. He has been staring at the same equation for 3 hours. His pipe is cold. His coffee is cold. The equation, however, is very much alive, and it is telling him something he is not sure he wants to hear. His name is Albert Einstein. He has 6 months to live. What he is looking at is a letter from his old friend Kurt Gödel, the same Gödel who had presented a rotating universe solution at Einstein's birthday conference 6 years earlier. The same solution that Einstein had publicly praised and privately found so deeply troubling that he wrote a lengthy response to it in the same conference volume. The letter contains a question that Einstein has been turning over for years without landing on a satisfying answer. A question about whether the field equations he published in 1915 contain, hiding in their structure, a permission slip for something that common sense insists cannot exist. Time travel, not as a metaphor, not as a loose analogy about memory or anticipation. Actual physical travel to moments that have already happened or that have not happened yet. The ability to step out of the river of time, walk upstream, and arrive in a yesterday that is just as solid and real and occupiable as the Tuesday you are currently standing in. Einstein died in April 1956 without resolving it to his own satisfaction. The question outlived him. And here is what makes it genuinely, productively uncomfortable. The answer, worked out over the decades since by physicists who took the mathematics seriously and followed it wherever it led, is not a clean no. It is not a triumphant yes. It is something stranger than either. A collection of theoretical mechanisms that are, each one of them consistent with known physics, each one of them facing obstacles that may be engineering problems or may be fundamental barriers. None of them conclusively ruled out, and each one unlocking a set of paradoxes so logically knotted that some of the smartest minds in the history of science have found themselves unable to untangle them. Time travel, as it turns out, is not a question you can dismiss. It is a question you have to live with. Before we go any further, drop a comment right now telling me where in the world you are watching this, what time it is there, and what the temperature is outside. I am going to come back to why that information is more cosmically interesting than you might think. And if you are new here, welcome to the channel. Subscribe and get comfortable. We are about to follow the physics of time from the equations in Einstein's study, all the way through wormholes, quantum branches, and the grandfather paradox, and discover that the universe has been quietly leaving the door to time travel slightly ajar, and has never quite explained why. The river and what lies upstream. We need to start with what time actually is. Not what it feels like. We all know what it feels like. The relentless one-way current carrying us from breakfast to lunch to evening, from childhood to old age, always in the same direction, always at the same rate. We need to start with what the physics says time is, because the physics says something quite different from the experience. Picture a river. You are sitting in a canoe somewhere in the middle of it. The current is carrying you steadily downstream. You do not need to paddle. You do not need to steer. The water does the work. Ahead of you, the river bends out of sight. Behind you, the river bends out of sight. And it might be tempting to assume that the river only exists at the bend you currently occupy. that the water upstream has somehow ceased to exist now that you have passed it, and the water downstream has not yet been called into existence because you have not reached it. Nobody believes this about an actual river. You do not need to be looking at a stretch of water for it to be there. The upstream bends are exactly as real as the bend you currently occupy. They are simply elsewhere, not observable from where you are. The physicists' claim about time is that it works the same way. The past is not gone. It has not been deleted. It is simply upstream, elsewhere in a four-dimensional structure that physicists call the block universe. The future is not unwritten. It is downstream. Your great-grandchildren are already there, at their particular coordinates in space-time, every bit as real as you are at yours. The past and future coexist with the present, the way the upstream and downstream of a river coexist with the bend you happen to be passing through. This is not a metaphor. It is the physical content of Einstein's special theory of relativity, which he published in 1905, and which dismantled Isaac Newton's comfortable notion of absolute time in about 40 pages. Newton's universe had a single cosmic clock, ticking uniformly for everyone, everywhere. Tuesday noon was Tuesday noon for an observer on Earth, and for an observer in the Andromeda Galaxy, and for anyone else in the universe simultaneously. There was one universal present. Einstein showed that this is wrong. Time is not absolute, it is relative. Two observers moving at different velocities through space will genuinely, physically, measurably disagree about the sequence of events. What one sees as simultaneous, the other sees as separated in time. What is in the past for one observer may be in the future for another. Both are equally correct. There is no fact of the matter about whose clock is right, because there is no universal clock. In 1908, the German mathematician Hermann Minkowski formalized what Einstein had shown and gave it the geometric language that physicists still use today. Space and time, he argued, are not separate categories. They are two aspects of a single four-dimensional fabric called space-time. Moving through space affects how you move through time and vice versa, because the two are not independent dimensions, but interlocked components of a unified structure. If space-time is a fabric, a four-dimensional block with the past, present, and future all laid out within it, then the question of whether time travel is possible becomes a question of whether you can move through that fabric in directions other than the one you are currently being carried. Whether you can go upstream. The answer from general relativity, Einstein's 1915 extension of the special theory to include gravity, turns out to be possibly yes, under specific and extreme conditions, in ways that are mathematically precise and physically uncomfortable and philosophically bewildering. Let us work through them. The first proof, muons and mountains. Before we get to the exotic mechanisms, the wormholes and rotating cylinders and cosmic strings, we need to establish something foundational. Because time travel is not purely theoretical. It is not a speculation limited to thought experiments and equations. It is happening right now, all around you, and has been observed in laboratories and mountain ranges for the better part of a century. Not backward time travel, forward time travel. But the distinction matters less than you might think. In the late 1930s and 1940s, an Italian physicist named Bruno Rossi became obsessed with cosmic rays. high-energy particles that rain down on the Earth's atmosphere from space, striking the upper air and producing showers of secondary particles. Among those secondaries were muons. Everyone you knew is dead. The city looks different. The technology is unrecognizable. You have moved 100 years into the future by spending less of your space-time budget on time and more on space. This is not forbidden by physics. It is required by physics. It is the universe being internally consistent. Now, the Kelly twins. Mark and Scott Kelly are former NASA astronauts who happen to be brothers born minutes apart. Scott spent approximately 520 days in orbit aboard the International Space Station over the course of his career, compared to Mark's 54. Because Scott was moving faster through space, his clock ran slightly slower. More time passed for Mark on the ground than for Scott in orbit. Mark, who was born first, is now further ahead of his brother than when they started. The gap has widened by roughly 5 milliseconds. Tiny, unmeasurable by human senses, but real, confirmed by atomic clocks, written into the experimental record of physics. Time travel to the future is established scientific fact. The question is whether the same basic logic can be run in the other direction. The second proof. Gravity bends time. There is a second and entirely separate mechanism for time dilation, one that has nothing to do with velocity and everything to do with gravity. And it is operating on you right now, at this moment, whether you are sitting in a ground floor flat or a penthouse apartment. Einstein's general theory of relativity, the extension of his 1905 work to include acceleration and gravity, contains a prediction that was startling when he made it and is routinely demonstrated in modern physics laboratories. Time runs at different rates depending on how deep inside a gravitational well you are. The closer you are to a massive object, the deeper inside the dent it creates in the space-time fabric. The slower your clock runs relative to someone further away. Time passes more slowly at the bottom of a gravity well than at the top. Picture a clock built from two mirrors facing each other, with a beam of light bouncing between them. Every time the light hits a mirror, the clock ticks. Now carry that clock into a region of deep space-time curvature. The light still travels at the speed of light. It has no choice. But the path it must follow is now longer because the space-time between the mirrors is curved. The clock ticks less frequently. Time for that clock genuinely passes more slowly. This is not a mechanical effect. It is not vibration or heat or wear. The geometry of space-time itself is different in a gravity well, and that different geometry means that time flows at a different rate. The practical consequences are not limited to thought experiments. Every GPS satellite orbiting the Earth is subject to two competing time dilation effects simultaneously. The satellite is moving faster than you are, which slows its clock relative to yours through velocity-based dilation. But the satellite is also further from the Earth's center than you are, which means it is higher up the gravitational gradient, and its clock runs faster relative to yours through gravitational dilation. Engineers must account for both effects in the satellite's timekeeping. If they did not, the accumulated error would make GPS useless within hours. The system works because Einstein was right. Now extend this to the extreme end of the gravitational spectrum. A supermassive black hole. the kind that sits at the center of most large galaxies containing millions or billions of solar masses, compressed into a region smaller than the solar system, creates a gravitational well so deep that the time dilation near its event horizon becomes extreme. An observer hovering just outside the event horizon of such a black hole, if they could somehow survive the tidal forces and the radiation environment, would age enormously slowly relative to the universe at large. Hours near the event horizon could correspond to years or decades or centuries far away. The physicist Kip Thorne explored this in the technical basis he provided for the film Interstellar. The scenario is not science fiction, it is the physics of general relativity applied to the most extreme gravitational environments that nature produces. This is the second confirmed mechanism for time travel to the future. Sit deep in a gravitational well, then return to flat space-time. More time will have passed in the outside universe than for you. You have moved forward in time relative to your starting point. Two mechanisms, both confirmed, both pointing in the same direction, which raises the question that this whole video has been assembling toward. Can the direction be reversed? The block universe and the permission slip? To understand why backward time travel is even on the table as a physical possibility, you need to hold on to the block universe picture we established earlier. If space-time is a four-dimensional structure with all moments, past, present, and future, coexisting within it, then the distinction between then and now is, in a specific technical sense, a matter of perspective rather than an absolute fact. An event that is in your past could be in another observer's future, depending on how that observer is moving relative to you. The same event occupying the same space-time location is past for one, future for another, and present for neither simultaneously. This is not a philosophical maneuver. It is a direct consequence of special relativity confirmed in every precision test of the theory. The relativity of simultaneity is real and measurable, and if the past is a real place, a set of coordinates in the block universe that genuinely exists, that things genuinely occupy, that light genuinely reaches, then the question of whether you can travel there is no different in principle from the question of whether you can travel to a distant location in space. Space travel is hard, but not forbidden. Time travel to the past might be hard, but might not be forbidden. The permission slip, the mathematical demonstration that backward time travel is at least consistent with general relativity, came from an unexpected direction in 1937, when a Dutch physicist named Willem Jacob van Stockum published a paper whose title was so technically dry it put most readers to sleep before they reached the result. He was working with Einstein's field equations, looking for exact solutions that described specific configurations of rotating matter. What he found, buried in the geometry of rotating infinite cylinders of dust, were paths through space-time that looped back on themselves. Closed time-like curves. A closed time-like curve is a path through the block universe that begins and ends at the same space-time event. A world line, the thread your physical existence traces through four-dimensional space-time, that curves back around and rejoins itself at an earlier point. If you followed such a path, you would leave a point in space-time and, traveling always forward in your own proper time, return to the same point in space-time, younger than when you left. Van Stockum had not built a time machine. He had found that Einstein's equations permit them, that the geometry of space-time in certain configurations naturally contains these closed loops, that there is nothing in the mathematical structure of general relativity that explicitly forbids them. This is the permission slip. It does not tell you how to build the time machine. It tells you that the laws of physics have not written one off. The Tipler cylinder. Frank Tipler was an American physicist who in 1974 decided to take the Van Stockum result seriously and work out what a realistic rotating object would need to look like to produce closed time-like curves. His answer was a cylinder. Specifically, a cylinder containing at least 10 solar masses, rotating billions of times per minute along its longest axis. The intense rotation of this much mass would warp the surrounding space-time so dramatically that a spacecraft following a precise spiraling trajectory around the cylinder would find its local light cone, the boundary of all the space-time directions available to it, gradually tilting backward. And if the light cone tilts backward, then forward motion in your own proper time can take you backward in coordinate time. You move forward through your own experience and arrive before you left. This is not a metaphor or a hand wave. Tipler worked through the field equations in detail and showed that they produced this result. A spacecraft that approaches, orbits, and retreats from a sufficiently massive rotating cylinder would find itself emerging from the journey before it entered it. The obstacles are severe. Tipler could only complete the mathematics rigorously for a cylinder of infinite length. He could not prove, with the tools available to him in 1974, that a finite cylinder, one that could actually exist, would produce the same effect rather than something slightly different that merely resembles it. This is not a minor technical gap. Infinite objects do not exist in nature. A result that only works for infinite cylinders is, in engineering terms, unusable. The cylinder would also need to rotate at billions of revolutions per minute while maintaining its structural integrity. No known material could survive those stresses. The rotational energy required to set it spinning would itself be extraordinary. And Stephen Hawking in the 1990s pointed out something deeper still. Hawking argued that producing closed time-like curves with any mechanism, including a finite Tipler cylinder, would require negative energy in amounts that dwarfed anything naturally available. Not merely very small amounts of negative energy, macroscopic amounts, quantities that make the vacuum energy fluctuations of quantum mechanics look negligible by comparison. Negative energy does exist. Quantum mechanics demands it. Pairs of virtual particles flicker in and out of existence, borrowing energy from the vacuum in a way that briefly takes local energy density below zero before the debt is repaid. The Casimir effect, measured in laboratories, is a direct consequence of this quantum vacuum structure. But the negative energy it produces is confined to microscopic regions for unimaginably brief durations. Scaling that up to macroscopic time machine territory is, as far as anyone currently knows, impossibly far beyond any foreseeable technology. But impossible and forbidden are not the same thing. The wormhole. In 1985, the astronomer Carl Sagan was finishing a novel. It was a story about first contact, about an alien civilization reaching out to humanity and inviting a single human being to travel across space to a distant star. Sagan wanted the journey to be scientifically plausible. He did not want to use faster-than-light travel, which special relativity forbids, but he needed to get his protagonist across 25 light-years without the journey taking 25 years. He called his friend Kip Thorne. Thorne was a theoretical physicist at Caltech, one of the leading experts on general relativity in the world. Sagan sent him the manuscript. Thorne read it in the car on the way to his daughter's graduation, worked through a few calculations, and called back with the answer. A wormhole. Picture space-time as a vast sheet of paper. Earth is at one end. The destination star is at the other. The straightforward route, traveling the length of the paper, takes 25 years at light speed. But general relativity permits space-time to be curved, bent, and warped by mass and energy. And if you fold the paper so that the two ends are brought close together, you can punch a tunnel straight through the paper that connects them. The tunnel is the wormhole. Travel through it, and you cover the full 25 light-year distance in essentially no time at all. At no point have you exceeded the speed of light. You have simply taken a shortcut through the geometry of space-time. Thorne showed that the mathematics was consistent. He also showed that wormholes could be used not just as spatial shortcuts, but as time machines. Here is how. Once the wormhole is established, you take one of its two mouths. Think of the wormhole as a tunnel with an opening at each end, and attach it to a spacecraft. You fly the spacecraft on a long, fast loop through space at close to the speed of light. The mouth of the wormhole that stays behind does not move. The mouth aboard the spacecraft moves very fast. Because of velocity-based time dilation, less time passes for the traveling mouth than for the stationary one. After the journey, the two mouths of the wormhole are out of sync. They exist at different moments in time, even though they are spatially close. Step through the wormhole from the stationary mouth to the traveling mouth, and you emerge not just at a different location, but at an earlier time. The time the traveling mouth experienced, rather than the time of the stationary mouth. You have gone back in time, not back to before the wormhole was created. That is a hard limit built into the mechanism, but back to any point after its creation. The technical barriers are again formidable. A real wormhole would be gravitationally unstable. The throat would snap shut the moment anything attempted to pass through it. To hold it open, you would need, once again, negative energy, exotic matter with properties that no known material possesses, possibly quantities that no natural process produces in the required form. Thorne and his collaborators worked on this seriously for years. Dozens of physicists have contributed to the theoretical framework. The literature is technically sophisticated and genuinely careful. The conclusion it reaches is not that wormhole time machines are straightforward. The conclusion is that they are not mathematically forbidden, and that the specific obstacles they face are questions of physics rather than of principle. Whether those questions have answers that permit actual construction is something nobody currently knows. The paradoxes. Now the story gets uncomfortable in a different way, because everything we have discussed so far has been about whether you can get there. Now we need to ask what happens when you do. Suppose you have a working time machine. You step in, set the controls, and arrive in the past. The moment you arrive, a set of logical problems start generating themselves, and they are not the kind of problems that go away when you think about them harder. They are, if anything, the kind of problems that get worse. The most famous is the grandfather paradox. You travel back in time. In the past, through some sequence of events, you prevent your own grandfather from having children. Your parent is never born. You are never born. But if you are never born, you cannot travel back in time to set these events in motion, which means your grandfather has children. Your parent is born. You are born. You travel back in time. And around it goes. The loop has no consistent resolution within a single timeline. Either you were born and went back and prevented your own birth, which means you were not born and could not go back. Or you were never born and could not go back, which means your grandfather had children, which means you were born. The logic eats itself. The bootstrap paradox is subtler and in some ways more unsettling. A time traveler arrives in the past carrying a book. The book contains a complete description of the theory of general relativity. Every equation, every derivation, every insight. The time traveler gives the book to a young physicist named Albert Einstein, who uses it as the basis for his work. Einstein publishes the theory, it becomes the foundation of modern physics, and eventually one of the physicists it inspires builds a time machine and uses it to travel back and give Einstein the book. Who wrote the book? Einstein copied it from the version given to him, which was copied from the published theory, which was derived from the book, which nobody wrote. The information exists in a closed loop with no origin. Of the behavior of quantum vacuum fluctuations near a forming closed time-like curve. As a time machine approaches the moment of activation, as the wormhole or rotating cylinder or cosmic string arrangement nears the configuration that would create a closed loop in space-time, virtual particles in the quantum vacuum begin to pile up. They travel around the loop once, then again, then again. Each circuit adds more energy. As the loop approaches closure, the energy density near the time machine diverges. It grows toward infinity. The time machine is destroyed by its own quantum vacuum before it can complete its function. The chronology protection conjecture is not a proved theorem. It is a conjecture. Hawking presented it as a motivated hypothesis, supported by calculations in specific cases, but not demonstrated as a general result. Other physicists have found configurations in which the vacuum buildup does not diverge, in which the chronology protection mechanism fails to engage. Whether these configurations are physically realistic or represent mathematical artifacts is disputed. What the conjecture does is reframe the question. Instead of asking whether time travel is forbidden by principle, it asks whether the specific process of building a time machine is blocked by the dynamics of quantum fields in curved space-time, whether it is the universe implementing its own protection against causal violation. Hawking was characteristically direct about his reasons for hoping the conjecture was right. He pointed out that the absence of time tourists from the future is, at minimum, suggestive evidence that backward time travel never becomes commonplace. If a working time machine is ever built anywhere in the future, its operators would presumably want to visit the past, including this period of history. We see no such visitors. The observation does not prove time travel is impossible. Visitors from the future might have excellent reasons not to announce themselves, but it is, at least, consistent with the hypothesis that no time machine is ever built. The many worlds escape. There is a way out of the paradoxes, or rather, there is a framework that makes the paradoxes dissolve. Not by resolving them within a single timeline, but by eliminating the condition that makes them paradoxes in the first place. The many worlds interpretation of quantum mechanics. Proposed by Hugh Everett III in 1957, the many worlds interpretation begins with a refusal to accept the standard picture of quantum measurement, in which a quantum system in a superposition of states collapses to a single definite state when observed. Everett argued that this collapse is an illusion. What actually happens when a measurement is made is that the universe branches. Every possible outcome of the measurement is realized in a separate branch of reality, and the observers in each branch see only their own outcome. The universe is not a single timeline. It is an endlessly branching tree with every quantum event generating new branches, each one equally real, each one inaccessible to the observers in the others. In this picture, backward time travel does not threaten causal paradoxes because the traveler does not return to their own past. They emerge in a different branch, a parallel version of history that diverges from theirs at the moment of arrival. In that branch, they can do anything they like. They can prevent their grandfather from meeting their grandmother. They can give Einstein a book of equations. They can press any button and make any choice. None of it affects the branch they came from, which continues on its own trajectory, causally intact. The grandfather paradox dissolves. The grandfather they eliminate is not the grandfather who will eventually produce them. Their own grandfather, in their own branch, remains undisturbed. The bootstrap paradox dissolves at the cost of becoming somewhat more complicated. The book of general relativity has a first author, a version of you in some branch, who figured it out independently. That version traveled back to a different branch and gave the book to Einstein there. In that branch, the book was given rather than discovered. But the information has a source. It was created in one branch and transmitted to another. The loop is not closed. It is open at one end in a different timeline. This resolution is not free. It requires you to accept the many worlds framework, which carries its own considerable philosophical weight. An uncountable number of branching parallel realities, each one equally real, none of them detectable from the others. Whether this is a solution or a replacement of one problem with a much larger one is, as with most questions in the interpretation of quantum mechanics, genuinely and unresolvedly debated. Between 2020 and 2022, the physicists Barbara Sheshelgi, Jared Wogan, and Jacob Hauser published a series of papers working through specific models, toy versions of time travel scenarios using simple objects like colored balls, and showing in detail how the many worlds framework resolves precisely the cases where single timeline consistency fails. Their work placed the many worlds resolution on firmer mathematical ground than it had previously occupied, and attracted significant attention in the physics community. It did not settle the debate. It sharpened it. Cosmic strings and quantum entanglement. The Tipler cylinder and the traversable wormhole are not the only theoretical mechanisms that have been proposed for backward time travel. Two others are worth examining because they extend the story in different directions. In 1991, the physicist J. Richard Gott showed that two cosmic strings, hypothetical, one-dimensional defects in the fabric of space-time, relics of the extreme conditions of the early universe, if they exist, moving past each other at high relative velocity, would warp the surrounding space-time in a specific and interesting way. A spacecraft following a precisely calculated path around and between the two strings, moving in a specific loop relative to them, would find that the geometry of the path brought it back to a point in space-time earlier than its starting point. Closed, time-like curves. Again, still consistent with general relativity, still without any explicit prohibition in the field equations, still requiring conditions. In this case, the existence and accessibility of cosmic strings and the engineering of a specific trajectory around them that are extremely demanding and whose feasibility is not established. Cosmic strings have not been observed. Their existence is predicted by certain models of the very early universe, the same models that predict magnetic monopoles and other exotic relics of the high-energy conditions immediately after the Big Bang. Whether they exist at all is an open observational question. If they do, they would be extraordinarily thin, far smaller than a proton in cross-section, but enormously long, potentially stretching across entire galaxies and carrying a mass per unit length so extreme that a single meter of cosmic string would weigh in the billions of tons. Finding one and navigating it precisely enough to produce closed time-like curves is, to put it gently, not a near-term prospect, but it is, once again, not forbidden in principle. Quantum entanglement occupies a different corner of this story. Entanglement is the phenomenon in which two particles become correlated in such a way that measuring the state of one instantly determines the state of the other, regardless of the distance between them. The correlation is instantaneous. The separation could be a meter or a megaparsec. It makes no difference. When one particle's spin is measured and found to be up, the other's is instantly found to be down, even if no signal could have traveled between them in the intervening time. This looks, on the surface, like information traveling faster than light, and faster than light information transfer, in the context of special relativity, is equivalent to backward time travel. The same mathematical structure that allows faster-than-light signals would, if used in certain configurations, allow messages to be sent to the past. But quantum mechanics imposes a restriction that prevents this. The measurement outcomes are random. You cannot control which result you get. You cannot encode a message in a random outcome. The correlation between entangled particles is real, but you cannot exploit it to send information faster than light, because the sender has no control over what the receiver observes. The channel exists. The signal cannot be placed in it. The back door to time, travel via entanglement, is locked. Whether it is permanently locked, whether there is some configuration of quantum systems that might allow controlled information transfer and thereby genuine backward causation, is a question that physicists continue to examine. No such configuration has been found. The current consensus is that quantum mechanics is structured in a way that may or may not be coincidental to prevent this particular route. What would it actually feel like? Step back from the equations for a moment. If you could travel backward in time, by any of these mechanisms, in whatever framework best survives future scrutiny, what would the experience actually be? Not the philosophical implications, not the paradoxes, the experience. What would you notice? You would notice, first, that you had arrived. The mechanism, however it works, would deposit you at a specific space-time coordinate, a specific place at a specific moment in the past. The world around you would be indistinguishable from an ordinary Tuesday at that historical moment. The laws of physics would be the same. Chemistry would work the same way. Gravity would pull things downward at the same rate. Nothing about the local environment would advertise that you had arrived through a mechanism that most people in that era would have considered impossible. You would notice, second, that you had a knowledge advantage of potentially extraordinary value. You know what happens next, up to the moment you left. Every sports result, every election outcome, every stock price movement, every discovery and invention. All of it is information you carry with you from the future. You would notice, third, that the question of what to do with that advantage is genuinely agonizing, because the many worlds framework, if correct, implies that any changes you make do not alter the timeline you came from. They create a new branch. The people in the branch you left, the friends, the family, everyone who knows you, are unaffected by anything you do in the past. You cannot go back and save someone who died. You can save a version of them in a parallel branch. But the version your loved ones know, in the branch you originated from, remains gone. If the single timeline framework is correct instead, if Novikov's self-consistency principle applies, if the universe enforces a single consistent history, then you cannot change anything regardless. Your presence in the past is already accounted for in the history you came from. Every action you take was already taken, and its consequences are already woven into the timeline. You are not a disruptive visitor. You are part of the furniture of that historical moment. You always were. Either way, the power fantasy version of time travel, go back, fix your mistakes, change history, improve everything, is not what the physics delivers. The physics delivers something stranger and, in its own way, more interesting. A universe in which the past is real, the present is a location rather than a special moment. The future may be multiple, and your choices, whatever the metaphysics of free will ultimately turns out to be, are made in a structure far richer and more intricate than the simple one-way river it appears to be from the inside. What we do not know. The honest accounting, as always, requires stating clearly what remains genuinely open. We do not know whether closed time-like curves exist in nature. The mathematics of general relativity permits them. There is no theorem that forbids them in all possible configurations. But no closed time-like curve has ever been observed, and whether the conditions required to produce one can be realized in the physical universe, rather than in exact mathematical solutions that describe idealized or infinite objects, is unknown. We do not know whether the chronology protection conjecture is correct. Hawking's argument was compelling and physically motivated, but it was not a proof. It was a calculation in specific cases, extrapolated into a general hypothesis. Other calculations suggest configurations where the vacuum energy does not diverge and chronology protection does not engage. Whether one of these calculations represents a genuine physical scenario or a mathematical artifact has not been settled. We do not know whether negative energy in the required quantities is achievable. The Casimir effect demonstrates that quantum vacuum effects can produce regions of negative energy density. whether those effects can be harnessed, structured, and scaled to the macroscopic levels required by wormhole physics or Tipler cylinders is unknown. The gap between laboratory Casimir measurements and time machine engineering is not merely large, it may be fundamental. We do not know whether cosmic strings exist. They are predicted by some models of the early universe and absent from others. No observational evidence has confirmed their existence. If they do not exist, Gott's mechanism is unavailable. We do not know which interpretation of quantum mechanics is correct, which means we do not know whether the many worlds resolution of the paradoxes is available. The many worlds interpretation is mathematically consistent and has a large and growing number of serious adherents among physicists. It is also deeply contested on both empirical and philosophical grounds. Whether the universe is a single timeline or a branching tree of possibilities is not a question with a currently settled answer. And we do not know, at the deepest level, whether the laws of physics as we currently understand them are the final word, or whether a more complete theory, one that successfully unifies quantum mechanics and general relativity, will have things to say about time travel that reframe the question entirely. The search for quantum gravity is ongoing. Its implications for the causal structure of space-time are not yet known. The door has not been opened. It has not been proved to be locked. The question that outlives everyone who asks it. Einstein pushed his chair back from his desk, walked to the window, and watched the students cross the lawn. He did not solve the problem. He left it for others, and others have carried it forward, and it remains unsolved, and it is, if anything, better understood in its unsolvedness than it was when he set it down. Here is what we know. Time is real, and it is physical, and it is not what Newton thought it was. It flows at different rates depending on speed and gravity, and those differences are measurable and have been measured repeatedly in experiments that no serious physicist disputes. The past is not gone. It exists at its space-time coordinates the way the far end of a river exists beyond the bend you currently occupy. The block universe is the picture that best matches the known physics of space-time, and within that block universe, the mathematics of general relativity permits paths that loop back on themselves, permits, in principle, travel from one point in space-time to an earlier point, does not, explicitly and demonstrably, forbid it. What it doesn't do is make it easy, or safe, or free of consequences that make your head ache. The paradoxes are real logical problems, and they have not been solved, only repackaged. The chronology protection conjecture is a serious hypothesis, and it has not been proved. The engineering obstacles to any of the known mechanisms are immense, possibly fatal, certainly unresolved. The question of free will in a deterministic or branching universe is as open as it has ever been. But somewhere between the equation